Yo, what's up, everybody? Welcome back. Today, we are writing a memory allocator, and we are on day two. Day two. So, yesterday, we wrote something that could map pages of memory from the system. We are kind of Linux or POSIX specific probably right now, where we are asking mmap to give us blocks of virtual memory that are aligned to some page size, right? We have our first attempt at a bump allocator or an arena or whatever you want to call it, something whose allocation scheme is essentially system, give me page. I get page 4096 bytes. But what if somebody allocate 4 bytes? You know? Well, we take our 4096 bytes, we put a little stick at the beginning of it, and then we take the 4 bytes and we put the stick here now. Wow. Then, every allocation, we move the stick forwards. Eventually, we hit the end and we go, uh-oh, need more memory. Another page now, please. And so what we do here is to make sure that we can unmap all of the pages, we put like a little pointer in here, back to here, right? And so as we move forward, we don't ever really care about, we don't ever have to start back at the beginning again. So we just kind of put a pointer backwards. Eventually we get here, and we support kind of like unmapping all of this, right? So if you reset this thing, we'll unmap all our pages, start from 0. But yeah, that's the bump allocator. Then we started using that bump allocator as an attempt to create something that's a little bit more intelligent. So a more intelligent allocator is something that supports freeze, right? So I have some memory. Maybe I allocate my 4 bytes, and then I allocate another 4 bytes, and maybe I free the first 4 bytes now. And I want to reuse them. If I ask for 4 bytes, I should be able to reuse this memory. So we started with the idea of I think it's called some sort of free list. We have a free list. We've got a list of stuff, and we go okay, we've got a range 0 to 4. That's chill. And then we go, okay, what's the next range? The next range would be 8 till big number. And as we allocate memory, we check the free list first. We say, are any of these blocks big enough to house me? And if they are, then hell yeah, we'll use one of those. And if not, we allocate a new page like before. And the free lists, I think, should... The fact that they don't point to a block seems a little fucking weird. Yeah, that seems like a problem. So, surely that's a bug. Surely, I think at the moment we probably only support one free list for the first block. Oops, that's kind of a fucking bug. And then we also don't merge the free list back together. So we don't if someone frees 4 to 8, we don't merge that back together. And when we free, we are right now just kind of writing whatever we freed back into the list. So we're gonna have 0, 4 duplicate in here. There's a lot of problems. We didn't finish, but we started to get somewhere. And so I think today's task is to finish that. Try to do some sort of experiment with something that has random memory patterns, and then maybe we can check fragmentation. How does this kind of get screwed over time? And likely the answer will be it gets very screwed over time. We're gonna have really fragmented memory, and we're going to probably use way more memory than we actually are using. So it would be nice to kind of look at that, and then we can try to use an allocation scheme that's a little bit more intelligent. There's this thing called the body system that is worth looking into, and then we can kind of see, is our fragmentation better or worse after that? That's the plan. I think we just jump in. We get moving and grooving. It is time. It is time. So, where did we get to yesterday? First of all, the first thing we notice just by looking at this, our free list surely needs to say which block this is coming from. Oh no, wait, our free list is pointer ranges. Wait, no, so this is actually totally fine, because we are not storing indexes into this block. We're not storing the free list as 0 to 4000 here. We're storing it as dead beef. I guess it's cafe food pointer to dead beef pointer. Right? These are literally literal addresses. So that means that this is fine, assuming that we never free blocks, which I think is pretty reasonable. Okay, so that's chill. So I guess the major thing to fix here is that our free list append here, we need to start by like find range, find free list elem or something. We need to find an element where this pointer comes from. Right, I forgot also that there's like alignment issues to worry about here. So in our free list, if we are asking for an alignment of like 4 and this is aligned to 2, we might like allocate from like here onwards, right? And so if somebody asks for like this array, what we do is we kind of like extend this by 1 and we say we write like a 2 here. And then we go like, okay, so now I know that when I look here that I should look 2 elements back, and that's the actual start. So there's like a little bit of like finagling to do there on free, but overall it's not too bad. Not too bad. Okay. So I think for now, let's start by not doing any of the like any sorting or anything in the free list. We'll just be like dumb stupid idiots, and we'll just iterate the whole free list and look to see if the thing that we are freeing can be like joined with any of the elements that are in the free list. I think that's probably fair. And then also we should probably do a second pass to check if we can merge those with anyone else. Okay, yeah, so let's do that. So let's do, looking at this, I actually am not convinced that there's anything wrong though. I don't think we should ever end up with duplicate segments. We should just end up with like really bad fragmentation. So we should be able to actually write a visualizer like right now and see how shit it is. Let's start there. We'll just say, oops, nothing to do. And then we will say, let's make a visualizer. Okay, so I guess the question is, what do we want to do? I guess we probably want to make some amount of random allocations and deallocations. And we probably want to vary the size by a lot, and probably the types too, because by varying the types we'll get different alignments, which is probably kind of useful. So let's do something where we have like, I guess this isn't visualizing it. This is probably more like building a test case, building a test system, and then later we will visualize. Okay, so what's our test system gonna look like? We're gonna have like alloc types, and I guess we're gonna be like, we'll have some U32s. I don't think we have to worry about like signed and unsigned here. We're really more worried about like size and alignment, right? So can we just do like U8 here, U32, maybe like a U8, U32, U16, and U size, right? That seems pretty reasonable. And in reality, we could have gotten away with doing, what's the word? Like we could have done like allocation. We could have like derived these from some number, but this is fine. I guess we could also do something that, I guess the alignment won't ever get bigger than this. Even if you have a big struct, there's no reason for the alignment to get larger than that, I don't think. Okay, so let's do like rand alloc. Okay. So this guy's going to take in some sort of like random interface, right? And he's going to output some allocation. And I guess this is going to be like a union backed by the alloc type. And so all of these guys are going to be like, Yeah, something like this. I guess U64 is probably a better word to use here, because technically use size in U64 could be different on like 32-bit architectures. And this is going to return an allocation. Okay. By want to reduce unhit error differs, do you mean that an allocator that returns errors less so you have to write them to begin with? Yeah, I guess the thought here is, let's open up my coverage port if we could find it. Firefox kcov index HTML. So the root the root problem stems from like this, where if I look at my coverage report, we just have like a bunch of error defers never run. All of these are like freeing memory, right? And so what I want to do is I want to remove these somehow or test them, right? Just like somehow make sure that like I don't have like unrun code in my code base. The idea of testing each of these is like daunting, but the idea of just deleting them sounds kind of nice. So what happens if we delete these error defers? Well, we delete these error defers, then this init function will leak if it fails. So what's the solution to that problem? Well, if like we had like a pool of memory just like one layer up, then all of a sudden, if we fail, we free that pool, everything's happy. And if we succeed, later we free that pool, everything's happy, right? So I kind of want like, I want some sort of like pool tree hand wavy. And what the design of that should look like depends on what an allocator does. And so we're kind of like on this like slight side quest to understand allocators a little better so we can design that tree a little better. You know? Can I like enum value? Oh, hell yeah, I can. That's hype. That makes sense. I run into that a fair bit. How did you get that kcov view? I think I just typed kcov. I think it was like, let's see if we have here. It was this kcov run my lint script. That's about it. Where lint is just like a program that just kind of hammers the application a little bit, and then I have some like excludes to make sure that like shit I don't want isn't in there. Okay, this is alloc type, and then depending on the alloc type, we return something different. So if we are like a U8, I guess we can do alloc size here. We probably want to limit this. So evenly distributed random integer that is less like in the range inclusive. This is inclusive, which is fine. So maybe we do like 1 to 1,000 or something. Sure. That seems fine. 1,000 is maybe a little big, but maybe it's not. Let's think. If we want to allocate stuff that's over a page large sometimes, maybe this has to get a little bigger. But for now, let's do it like this. I wonder if we can do like I wonder if you can do like alloc type. Can we get clever? To type. Wait, this sounds like it might actually work. So we switch on self. No, because this will depend on a runtime value. Yeah, we wouldn't be able to do this and this was a comp time self. And I don't think that we have comp time, so we're not so lucky. Not so lucky. Oh, wait. No, this will work. This will work. Because here we can get the comp time value by switching on this thing. Wait, so that's hype. That's hype. So we can do U8 returns U8, Q16 returns U16, U32 returns U32. This is crazy. Who could have seen this coming? U64 returns U64. And I wonder if we can kind of do this. No, to type. I think that makes sense. Then we can do inline else here, which will give us, which will like generate switch branches for each of the tag types. So this will give us just like tag, right? And now we can get a little crazy. We can, since T is a switch, T is like comp time known now. And so you can do like T to type, and then we can allocate with this thing. Alloc size of, or this many things of alloc size. Data is this, and then we can get even crazier. Stood mem here probably, and we can say return me a union of type allocation that is initialized with the tag name of T and with the data of data. And this will create like a branch for each of these things, and I think that kind of works. If that works, that's fucking sick. Otherwise you would have had to like type out every single one. Not that typing out every single one is a lot of work. In fact, this probably took longer, but I just like this conceptually more. Okay, so let's make a main loop that like does something with this stuff. So maybe we create our RNG. Rand default pseudo RNG initialized with 0 because I don't really give a shit. Yo, that's crazy if it works. Yeah, right? Okay, we get the random interface out of this thing, and then we put that into rand alloc with alloc and RNG. And then we probably can do like dinit here. Okay. And it's really just like switch self. How does this work? Alloc free. It's any type. So we can just literally do like inline else, which will create a branch for each of these things again. And then we can just do like alloc free data. And I think that works. Because then we can just do allocation dinit here. Okay, let's just see if that works. Could also use stood meta field type or at field type on master. For what? For which one? I'm not so sure. Stood meta field type. So this returns a type based off of the info. Oh, I see. So you could like get the field type of the allocation side of something. Yeah, I see what you're saying. Okay, so does this like work? No. So, because here we need to maybe fail on this thing. That compiled, which is hype, and nothing like really blew up on us. Okay, so let's now just try to do something like maybe we want to have like a rolling buffer of allocations, right? So what's the easiest way to do this? Can we do this cheaply? Const rolling buffer, I think we can call this. And all this guy has is like some items, which are going to be some capacity of t's, which means that this has to be a function, which will take in a t and return a type. Okay. And he's going to have an index into this thing. Okay. And so then all we have to do is like initialize this thing with some size of how many items we want to stick in this buffer. So we're going to have some allocator come in. And we are going to return a rolling buffer, except it can't be called rolling buffer here. It needs to be called self because rolling buffer is the function name, not the type name that we're returning. Okay. Then we ask for like num items. Index here is going to be 0. And then we probably want like default val here as well. I think. Let's think for a second. What are we trying to make a rolling buffer of allocations? We could just like seed this so that it's always full, and then we don't have to think about the empty case. Let's do that. Initial state. So in fact, we can kind of just do this, and then all we have to do is implement push. Okay, so push is going to return back the thing that came out, and we're gonna say like ret is self items at self index, boom, and then we return ret, and then we just say self items at self index is equal to element, boom, and which means that we actually have to take an element here. Okay, so here we have t chill. So now we can make a rolling buffer of allocations. Okay, so and we just have to like seed him. So we take the like allocations buff, and this is gonna be an allocation of 100 allocations. Okay. For allocations buff, we initialize this thing with a random allocation. Allocation. So here we go, like allocation dot stars equal rand alloc of alloc and rand. Bing, bang, boom. Okay, so now our allocations is this thing where the items is the allocations buff. Boom. And now we should be able to start just like pushing allocations into this thing. So like for 0 to 1,000, we like just push into this buffer. Right? So we're like, here is a new one of these guys. Yeah, I think that this surely has to be tried, right? Yeah. Slap a new guy in here. And then we get the like evicted and we free this guy. All right. Seems pretty good. Seems pretty good. So now we should be able to inspect the state of the allocator down here. And I guess it would be nice as well if we could like check that the allocation is still like good. So maybe what we do, like to avoid like if our allocator is like fucking up and like giving out ranges of things that are still in use, we should fix that. Or we should yell about that. So I think probably here I think it's good enough if we go for data 0 data len, we say like data I is equal to I. I think that'll be fine. And so then on eviction, we can check that for 0 evicted len, we should check that evicted I is equal to I. If this is not the case, return error, maybe we unreachable. So that if we're in this state, we can check, we'll look at it in the debugger. We just like hard fucking crash. Yeah, let's see what happens there. So we got I always get this type backwards. It should always be typed first. I don't know why I ever do anything else. This it equals I needs to be int cast because this is for many types out of a U size. Which means that it actually has to be I percent stud math max int of the type. Because a uint or UH can't fit 1,000. So I think that should be fine. And then I guess we actually have to intcast this for some reason. Okay. 288 is mad because the rolling buffer has to be mutable for this to work, but I don't think it actually does. So we can just write const here, which is fine by me. Evicted len does not exist at 289. Why? Oh, because this is an allocation. Fuck. Which is like a generic type. So we have to, shit. I guess we look at the individual type. Can we do the same trick here? We might be able to. Because they're all kind of, like, the shape of all this data is the same. So we can probably get away with that. Hell yeah. Okay. So now we are hitting this case, which is bad. That's not good. So can we take a little peek skis at what is going on there? E does not exist. Fuck you. Oh, fine. Fine. We'll go to the right part of the backtrace. Little bitch. Okay, I shouldn't have been so mean. Sorry. Yeah, so it does look like we just have like zeros, huh? Oh wait, 0, 1, 2, 3, 4, 5, 6. Wait, maybe this is fine? This looks okay to me. 1, 2, 3, 4, 5, 6, A, 10, blah, 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 blah. It would be nice to know which element is failing here, because to me this looks okay. Actually. Oh, we actually can check, huh? Oh, I'm an idiot. This is just a bad check. We need to check that this is I, percent std math max int of t2 type. Yep. Much better. Okay. So that's a good sign. That's a really good sign. That means that at the very least our allocator is working, right? Now the allocator state is probably just like fucked. Does Zig also check types when comparing? Yep. I don't think it knows how to compare if the types are not the same. So what we're doing here is like we're being like really clever with our types, but it's fine. I guess maybe like here it might be upcasting the UH to a U size or something. That might be what's happening. Yeah, it probably is. So can we actually like dump our allocator state now? Let's like take a little peek skis of what the allocator state looks like at the end. So we have a fair number of blocks here. What is this? This is like 65 blocks? Well, yeah, something around on the order of like 42 blocks. We have a lot of free chunks, right? So it looks like we're very likely not doing a very good job of reuse. And then it would be nice to print some stats out of this thing. So let's just start maybe by, let's call this inspect allocator state. So I want to see like maybe one, it would be nice to know if if the allocated stuff plus the free stuff equals the number, like the amount of stuff we think we should have. That's probably a good thing to check. So maybe we can say like total allocated, and the amount of free stuff, like currently allocated, we can keep track of. Then we can keep track of the list of free stuff, and then we can compare the two. And then it would be also nice to keep track of like how do I say this? When we allocate stuff, because of alignment, we might have this case, right? Where like we have a buffer of this size, but they need to be aligned to here, right? So it would be kind of nice to write down how much wasted space there's, or like at the very least like space lost due to alignment, and then maybe space lost due to like tracking. So alignment wasted, and tracking wasted. And then we can also write down a requested, like requested allocated. And then what we should be able to confirm that if we add these three numbers up, we should get this number. And if we add up this number and this stuff, we should get this number. That's what I think should happen here. And let's just start tracking all that stuff. I guess we should have said that this started sometime before now. Okay. So every time we allocate, we just have to start thinking about this stuff. Okay. Let's think here. Len with tracking is len plus 1. So here we map a block, and what happens here? We return a pointer to that thing. So the current self currently allocated plus equals len with tracking, because we're going from the start of the block, so there's no like wasted space due to alignment. Tracking wasted plus equals 1, right? Because len with tracking is 1 larger than the length that they asked for. Cool. So that's fine. So now we also have to do the same thing here. So I think what we're gonna do, we're gonna pass in probably parent is normal alloc, and then we can pass in self here, and then that means that here we can do the same tracking. So we are giving a slice of like something that we found on our free list, stuff that's previously been freed. Spherephoria, my beacon among the sea of endless web slop. Hey, I'm some web slop too, baby. It's web slop everywhere. Okay, so here there is alignment stuff. So the parent alignment wasted is equal to the align start minus the start. Okay? Chill. Maybe we should only do this here probably when we actually return. Currently allocated. Oh, we also have to add requested allocated. So this is len. Okay. Currently allocated plus equals align end u minus start u. Okay. So this is the total stuff that we lost from this. That's alignment wasted, tracking wasted. Is 1. It's always 1. And then we'll just note here, note len is equal to len with is already has the wasted, the tracking segment included. Okay. And requested allocated. Plus equals len minus 1, I guess. Which is kind of, this is like just a bad way to keep track of this stuff. So we'll just put a fix me on here, like, ew, we shouldn't have to do this plus minus 1 shenanigans. But, you know, prototype mode. In prototype mode, we're allowed to do whatever we want. And we claim that it's okay because we say we're prototyping. And when we say we're prototyping, we can write whatever garbage we want, and it's okay. Okay. So now if we just look at this, I guess we want to have some way to like count free bytes. So I guess we probably in like dump allocator. Maybe we should have some function that's like total block capacity or like total capacity of the of our normal allocator, our very normal allocator. And so this is going to iterate over all of the blocks. Probably that we have pulled, and I assume that these blocks have their size. Yeah, they do. So we just say var ret is equal to 0, ret plus equals normal block list get I len, and then we return ret. Okay. And we can say total free list size, I guess we'll call it. And this is just the same thing, but it's free list. And we're probably looking at like free elem is this, or this is called range, I guess, is what we call it before. And then we get like range end minus range start. I think that that should be okay. And so now when we dump the allocator state, we can do like total allocate, like block size of allocated blocks. That's a good name for this. Is going to be total capacity of normal. Boom. And then we can also check the ready to be allocated is going to be the free list size. And then we should check that the currently allocated is just normal currently allocated. And then what was the other stuff in here? All of this stuff. Okay, so let's just start with a std debug print. We copy this stuff. We put a number, and then we paste it. Boom, and then I guess we'll just leave it like that. Normal dot in front of these, we forgot. All right. Range and rate minus range start. He doesn't like this. Interesting. Does this work? Do we really have to do it like this? Kind of blows. Kind of blows. But it is what it is. Okay, we should put some new lines, huh? Probably. Okay, so size of allocated blocks. Am I crazy that this is too small? This says 3, 6. This is 2 megabytes. And he he thinks that we have because we need to subtract from currently allocated when we free. It's a pretty good point. Self currently allocated minus equals what? Buff start u is buff start buff and u from buff end. Then we need like, I guess we can actually just do we have the requested free size is equal to buff len. The actual free size is equal to buff.len plus start adjustment plus 1. for the length. Then we say tracking. Oh, we have to update all of our tracking variables. So it's literally like so tracking man, bro. Shut up, man. Okay. Currently allocated minus equals actual free size. Requested allocated minus equals requested free size. The alignment wasted minus equals start adjustment. And the tracking wasted minus equals 1. Okay. Let's see if those numbers all kind of line up. So here we see that there's this much free. I guess we can just do the check, right? So we can just say all bytes accounted for. And this is like, so total capacity is this. Const free list size is equal to this. Oopsies. I thought I was in the right braces. I was not. Okay, then we just say that the normal dot currently allocated plus free list size equal to total capacity. Fine. We'll put you in a fucking struct if you want it. Good evening, good evening. All bytes accounted for false. So that's not good. That's not good. The question is why? Are we like, how far off are we? Like this. We're off by like 1K ish. So that's not good. How much false? Yeah, I guess we could write the problem. We could write minus this and then as an I64. So we could do it like this. Which should be fine. And then as I64 as this. Okay. Yeah, so we're off by 1,000, which is not, it's like a weirdly round number. Like a very strangely round number. Is it like always like that? I suspect that it's related to this 1,000 would be my guess. Do you think it goes to negative 2,000? Yeah, it does. So we have an off by 1 somewhere, probably on our free, probably. Alignment wasted minus equals start adjustment. So it's what is our thing? It's currently allocated free list size and total capacity. So buff start minus start adjustment, buff end plus 1. Boom, baby, let's go. We were off by 1. Off by 1 on our free list. We forgot to put our tracking variable back into the free list. But now we're fucking chilling. So at the very least, we have like some confidence that our current allocator works. Whether or not it's like good, right? That's a totally different story, right? We have like the fact that we have 700K just sitting there in the free list is like a problem, right? This is 700K of like fucking wasted space right now. But it's not bad. Not bad. It's at least like working. We have no evidence at this point that we are overwriting wrong memory or giving out memory that is not allocated, which is good. So I think now I want to visualize this thing in some way. I would love to take a look and see like maybe on like a line I don't know how I want to represent this, but we're gonna have like some list of like free ranges, right? And I guess we're also going to have some set of like non-contiguous blocks of memory that we've asked for from the system. They might be contiguous, but they also might not be. So I guess maybe we want to show, maybe we draw like each block, maybe like with some like scaling for its size, and we show in it like sections of free memory. So maybe we color this thing red by default, right? We say this thing is like fully used, fully fucking utilized, baby. And then we go, actually according to our free list, this section is totally fair, and this section is like totally fair. Maybe this is the visualization that we need. Which sounds kind of reasonable. Seems reasonable. So maybe at the end of this, we just dump the allocator state into a JSON file, and then we can like open a web page that looks at it. Old school HD defrag UI? Is that what it looked like? Windows 95 defrag. Dude, Windows 95 defrag simulator is a crazy... Is that like a game? Dude, that's so funny. I guess they were working in pages, and we're not. So they kind of had a little bit of flexibility there that we don't have for the visualizer, I think. Okay. So can we just like dump this? I think blocks are... Yeah. I think we might be able to get away with just like std JSON dumping this thing and then loading it in a web browser and looking at it. That's kind of funny. Stringify, and we stringify the normal alloc with some form of options, like you know, white space is equal to, indent 2, because I want to be able to read the JSON with my eyeballs. And then this has like some sort of like writer, open create file, I guess, because we're writing it, output JSON, or allocator state JSON. And I think I'm gonna actually put it in res here because I'm going to throw some like HTML stuff in there. Visualizer, sure. Seems reasonable. This has to be tried, and then otherwise I think we're chilling. Okay. He's mad because someone wants a try here. And then unable to stringify type without sentinel. Oh. Oh, because he's actually trying to stringify... Oh, that sucks. He's trying to stringify like an array like it's a string, which we don't want. So I actually think there's an option for that. Omit strings. I guess I don't even want the string. I want like the pointer address. Which means that we can't do it this way. But what we can do is we can just output a thing that's like that follows the shape of this. So we can get like JSONable. Returns a JSONable. Look, we're not going to be picky about this right now. So this thing, I guess, returns a slice of U sizes for this thing. Each block is going to have, I guess it's more like each thing, I guess we have, okay, block. JSON block. This thing has a start and a len, right? Okay. Each thing in the free list, JSON range is literally just gonna have like start, usize, end usize. I guess we could just do both of these things are JSON ranges. That way we don't have to like make two types for this thing. Okay. And then these are all the same. Okay. So then when we create this thing out of ourselves, we probably need an allocator. We go like, hi, Zig, question mark? Hi, Zig, exclamation mark. Hi, Zig. Hi, Zig. Maybe with a, hi, Zig. Oh my god, stood out or something. I don't know why that's getting colliding, but we'll just do it like this. Okay. So we need to, I guess technically this guy needs a dnit if we're gonna be, it doesn't matter. It doesn't matter. Let's not get ahead of ourselves. So stood alloc, we need however many things are in the block list. We need this many of them. And we want them to be JSON ranges. Yeah. Like this. Okay. Cool. So be careful saying those words flipped. Oh my god. Yeah, dude, for real. Jesus. It keeps happening. Okay. So the block list, we have the free list, which is the same, but with the free list here. For 0 block list len, we go from self. We say that the block list at I is equal to the thing in the block list that we actually use at I, but we have to like convert this thing. So we say that we have like item is this thing, right? Boom, 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 boom. And then we need to convert. So it's start is equal to item dot pointer int cast like this, and then the end is equal to item pointer plus item len int cast. Okay, so that kind of covers the block list stuff. Then we have to do the free list, which is the same. We just have to do some int casting. So it's free list I is item dot, I think it's just start and end here. Yeah. Okay, and then we can return this thing. Boom, 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 boom. And then we take the rest of these things and they just come from what, like self dot paste comma, something like that. Something like that. Okay, so now we should be able to stringify at the very least normal JSONable. All right. Are you developing your own malloc? Yes, I think that's hand wavy the right. Yes. It's not technically malloc, but it's very similar to malloc. Expected integer. Oh, it's not int cast here. It's int from pointer. Fine. Fine. If you're gonna be that way, int from pointer on probably both of these, all of these, I guess. Free list, he expected this thing, found that thing. Oh. Oops. Okay, unable to stringify type this thing that we didn't type try on. Fine. All right. This looks reasonable. Yeah, so we have block list. We have currently allocated, request allocated. Yeah, this seems fine. This seems fine. It has everything that we need. Everything we need. Okay, so now let's write a visualizer. Visualizer index HTML. We look at the source of any web page to copy. Can we just like copy, paste? Yeah. HTML, and head, and we do the body, hello world, and I guess we just go here. Okay, cool. Hello world. We are chilling. It would be nice to have like autocomplete here, so I think I'm going to pull in some of those packages that we use for this stuff. Probably here we want like this, and we want to edit image editor shell and paste them in here, just for some nice little autocompletes. Just for some autocompletes. Give him a sec though. He's got to think. He's unpacking archive 8001CC402F61B8FD65. Okay, thank God, dude. I didn't want to read the whole thing, but I was ready to do it. Okay. Okay, so if we go visualizer index.js now, we want to do like window on init or on load equal to init or something, and then we do like async function init is like the way we usually do this, and we say hello world here as well. And then I guess in our index HTML we have to load that script, so we have to go hello like this, refresh, control I, console, hello world, we are so chillin'. Do you make all of your money from streaming? Just wondering how you have this much time to do fun stuff. I'm just burning cash, dude. Like, we're just like ripping through it, which is fine. I don't mind. It's this was the plan. This was the plan. I didn't feel like working anymore for a little bit, and I was like, well, we can just not, right? It turns out you have that choice sometimes if you're fortunate, like me. I'm very, very fortunate that I got to work as a software developer for 10 years and save a lot of money. So we have some time. Obviously, someday I'll have to work again, but not today. Okay. So I guess if we want to draw some stuff, surely we want to make a canvas to put some stuff on, right? Is it just like this? I think probably. And then we have like ID equals canvas. And then in our JavaScript, we try to use that canvas. And I think that we figured out that you can do like some type annotations here so that it figures out what the fuck is going on. What is it? Get context. We want like a 2D context for this thing because we're not going to do any WebGL stuff now. We're getting a little lazy, and we fill a rectangle of this thing from 0, 0 to canvas width, canvas height. We fill it with red, probably. And if we are there, bam! Okay, so we have everything we need to start drawing stuff. So let's start rendering out. Let's start running out some data. I guess first we actually need the data. So what is this? What do we call it? Visualizer allocator state. Await. Response. And then we do like response JSON here. Okay. So I guess it'd be like this. And then can we just for now do something silly like replace the content of this thing with the JSON. Okay, so he definitely... What the fuck? Are you fucking kidding me? Are you kidding me? I can't fucking get JSON? Oh, is it just I can't fucking fetch anything from JavaScript here? Did you know that elements with an ID in HTML are automatically available on the window object? That's pretty cursed. I did not know that. That's crazy. Oh, await JSON. I mean, either way, it's denying us, but thank you. Good eye. Jesus Christ. Okay. It's fine. We'll start an HTTP server, I guess, because, like, that's what the fucking world needs us to do. Fucking cores. Herflock, thank you for the tier 1. Much appreciated. Let me help with that hype. Thank you. Not necessarily, but appreciated. Okay. So, where the fuck are we? Here. Can you run this thing with disable caching? That'd be hype. No. Well, we'll live. What is it? 880? No? 8,000? I can read. That makes sense. He did just replace it with object. That's fair. Can I, like, stringify? Stringify JSON JavaScript. Literally just JSON stringify. He doesn't like that. Fucking lying piece of shit. Oh. Okay, sorry. He means like this. There we go. That's our shit. Okay, so we do have everything that we need. How do we make it so that, like, do I just have to have this open to disable the cache? Is that how this works? I can't remember, but I think it is. So I'm just gonna leave it open just in case. Okay, so now let's start rendering some stuff. So I guess the first thing to do is render each of the blocks. So function render block list blocks, and probably the context as well. So then we have to tell it what is it? It's param context is an HTML canvas context rendering context 2D. There we go. For let I equals 0, I less than blocks length, I think that's how this language works. Can we set shift width equal 4, set tab stop equals 4? There we go, that's better. Fetch cache no store. Nice. That sounds sick. But that won't apply to the, like, HTTP stuff, right? But I guess that doesn't really, maybe that's fine. Or the HTML, I mean. Sorry, brain. Okay. So I guess for each block, I guess we're going to measure the, like, max block length here. It's end minus blocks I start. And we take the max probably, yeah, nice, of max block size and that, okay. Then we should have a max block size, so then we can just go, like, blocks. We'll just start with the 0th one for now, and we'll look at his end minus blocks 0 start. How do we do this? I guess we start him at 0. Yeah, probably something like that. So we start him at 0, and then his width is going to be end blocks 0 and minus blocks 0 start over max block size. And we're gonna hope that this doesn't do integer division, but I don't actually know. And then the height is probably gonna be like 50 or something, right? Okay, so let's make sure that when we clear the screen, we clear it with create with white, and then render block list. JSON blocks. Okay. And the context? All right. I guess we did still do this. Okay. Refresh. Not looking good. Not looking good. What's he pissed about? Blocks is undefined. How? Oh, it's block list. That's why. That's why. JavaScript doesn't have integers, so you're good except for big int. That's what I thought. So that's kind of hype. So here, this block list is like, looks like way, like, you know, impressively small. Impressively small. So, what the fuck? I'm not doing something stupid, am I? Console log max block size 8192. And what is blocks? Yeah, so surely this is wrong. Times CTX canvas width. There we go. That's what we're looking for. So this is half the thing. I guess, can we make the canvas like maybe gray just so that we know where it ends? There we go. So we have a block here that's like half the canvas width, which makes sense. Cool. So I guess we want to start with our y at probably like, you know, 10, and then like we want to iterate over for each block. I guess we can do, it's actually, you can do this, right? For let block of blocks. I probably should have done that way, I forgot. So this is a block here, the y is y, and then we do y plus equals, I don't know, block pad. All right. Not good. Because this has to be plus block height. Okay. Better. Okay. Then presumably our canvas just needs to get big. How many of these things are there? I guess we could just make them smaller. Bro, how many of them are there? Okay, we finally ran out. Okay, cool. Cool. So I'm fine with that. That's fine. That's fine. Okay, so now we have to. I bet you this like rails my compression, huh? Okay, so now we have to render the free segments on top, right? So I think that we render the blocks as red, and then we can kind of shove the free list here. We don't have to worry about this, except we do probably have to store the max block size here, which means that probably here we want to return max block size for now, or we pass it into both places and calculate it somewhere else. Yeah. I think that makes more sense. Because then we can just pass them both here. Const max block size is equal to calc max block size with JSON block list. Then this could pass in here, and then we can render the free list as well. Okay. So now we should be able to figure out where everything goes kind of automatically. So let I guess we probably need the block list here as well, actually. Because for each item in the free list, we have to figure out which block it belongs in, which is not really trivial right now. We can just do like an n squared search right now, or not n squared, n by m search, because I don't really give a fuck. I'm sure it'll be fast enough. But it's worth checking. Okay, so we can say function like block for free item. Block for pointer, we'll call it. And in here, we have to be like, we take in a pointer and we take in the block list, right? And we return a block. We don't have to write that down because JavaScript is a shit language. We go for let block of block list. Now, don't forget that you don't do let of in block list. You have to do let block of block list because they mean two completely different things in this shit garbage fucking language. But here we just say if pointer is greater than block list start and pointer is less than block list end, this is probably allowed to be greater than or equal to, but not allowed to be less than or equal to. Return pointer. Return block. We probably actually want the block index. Because this is going to be used to compute the height. So we actually return I here. Block index for pointer. And then here we return null. And then here we go for each free item, we get the block index for the pointer, and we take the free item start. And the block list, this will give us block index, and then we just have to figure out the y value from this. So y is going to be the block pad plus I block index times block height plus block pad. I'm pretty sure this is where it goes. Pretty sure. And then the block offset has to be calculated somehow. What's the difference between in and of? I think it's like in will iterate the fields of an object, and of will iterate the elements of an object. Which is like semantically different. So if you have like an array in JavaScript, it might have a field in it like it might have a field in it that called length, right? And if you do in, you're going to get length, and if you do of, you're going to get like some like iterator type. It's some confusing shit like that. Okay, what do we do for our x value? X here must be like relative to the max block size, so we probably want to go like block start is block list at block index start, right? And the x value must be like the free list start minus block start, right? Divided by the max block size times canvas width. Okay. And the x, this is x start, x end is just the end of this thing. Okay. So then we can say that we get x start here. We get x end minus x start here. The block height is the same. Y value is calculated, and we don't have to do y plus equals here. Okay. That's like a maybe. Unlikely to be correct, huh? Unlikely. Block index is undefined. At index.js 39 is if block index equals to null, throw error invalid block ID. Okay, so we are getting the case where we can't find this thing, which is not good. That means that like our block list, can we like print maybe the free item start? Okay, and then can we look at the block list? Jesus, these numbers are gonna be hard to find. JS objects are like dictionaries. In or object keys returns keys. Of returns values. Arrays are dictionaries where keys are integers. Well, you get the idea. Yeah, nice. That's a good way to say. That's a good way to phrase it. Okay, so can we, I guess, look through the block list? Can we just go like allocator state? And can we look for Jesus Christ? So I guess we want to like iterate over all these things and print for JSON block list. No, let block of this thing. We need to like look at the block. Block start, block end, and then like what is this value? This thing is greater than block start. Let's just do that. That will help us understand. This doesn't happen though because it's after the failure, so we just do it here. Boom. Okay, so the pointer is greater than every single one of these things. Can we sort these by start? Are they sorted by start already? No. Unless they're sorted the other way. It looks like they kind of increment in value going up, which is kind of nice for us. It also looks like they are contiguous, which is kind of interesting as well, but we can come back to that. So we have pointer value 1402. So this is 8739. 78739. 78739? Okay, can we like copy paste these numbers and bring them down here? 140 2824 737 737 87392 87389. Yes, this is just out of bounds. This is just bigger than this. So how the fuck is that happening? Think you're not passing all the parameters to render free list? Dude, fuck. That's true. Fuck this garbage fucking language. But I mean, it's still happening. Right? Like whether, I think that this is, can we do like, and this is less than block end? Oh, there is one. Okay, maybe I'm fucking stupid. Okay, so there should be one. There should be one. Context, free list, block list, max block size. Okay. So this is still failing? Oh, because I'm a dumbass. Dude, this language sucks balls. It's so bad. Okay, so can we just try rendering one of these? Let's just pretend. So I guess can we, let's say we print out what we're trying to render here, because clearly it's not working. We do see some nans in here, so get fucked us. Blocks. So which of these like fucking million things is a problem? Max block size. That's fine. CTX canvas, width, block start. All of these seem fine. Free list start. Oh, I'm a dumbass, dude. This language is so bad. It's so bad. I mean, like, I get it. Like, I should just not suck. But, like, come on, man. Okay, so red is allocated, blue is free, I believe. I guess we should be careful about drawing incorrect conclusions from this because rendering the JSON itself is taking some memory from the allocator that we're logging from. So can we just use a different allocator here, or just make sure that like maybe we're yeah, this is tricky. Let's just use a different allocator here. GPA, general purpose allocator. And then we can use that one here. Okay. I mean, it does seem like that is still happening. So what are we seeing here? We're seeing like a fuck ton of free memory with like small amounts of red scattered around, unless those are caused by like floating point imprecision, which I kind of doubt. But I guess it's possible. I guess what would these be? Yeah, I don't really understand where all of these tiny little allocations are coming from. So it seems to me like there might be a problem, but I mean, yeah, I don't know. I don't know. Indicative of a bug. But definitely like this is a problem. Right? So let's try um let's try just making any attempt to like merge adjacent elements in the free list. It can be slow, it can be stupid, it doesn't matter. We just have to try. So let's make our allocator go where is this guy? Here. Merge adjacent elements. Merge adjacent free segments. And if we do this every time we free, then in reality, it should only be stuff that touches our last element, right? So I guess maybe this takes self free list size -1 or something as like the index of the element that we're trying to merge. Uh-huh. Okay. Which I guess is kind of like this. Okay. And like we said, free, like, it, like, inserted index, index, I guess. Sure. So I guess, what do? We, like, iterate over every element in this free list. Uh-huh. So I guess we want like our LM is free list get index. Okay. Other. Okay. And if other lm start is equal to our lm end, or other lm, I guess these are kind of different cases. So in this case, what happens? We do like other lm end start is equal to r lm start. Okay. If else if other lm end is r lm start, we do other lm end is equal to r lm start. Okay. Chill. Now we have to like swap remove our like index and then go again. We could do this, I guess we might as well do like a var iterators idx or something, and then like do this in another loop. Outer loop here. Okay, then we get the element here. Then we do it is equal to I guess. And then continue outer. Okay, that seems reasonable to an extent. And then, is there anything else we have to do here? We need to break out of this thing. Yeah. Okay. Swap remove it. Yeah, that's a good point. We should just kind of ban use of index here. It would be cool if you could have like a language feature that was like, don't let me fucking use this variable anymore. I feel like I hit this type of mistake often. Other element end equals r element end. Yeah, that's true. That's true. Lots of mistakes here. Thank you, chat. And I guess we do have to implement swap remove. So we have this like linked arrays list that we implemented in happy hour today. It was very similar to like the split list we had yesterday, but this is like kind of like a list of arrays that are allocated, that could be allocated by like a bump allocator over time, right? So you're gonna have stuff that's like, I'm gonna have like some chunk of elements here, then when I run out of space, another chunk of elements over here, then when I run out of space again, we'll allocate like more stuff over here, right? And then what we do is we store like the starts of these guys, boom, and that's kind of what we're seeing here, right? So we have blocks is a double nested list of t, so this is like each block, and this is like the list of blocks. We can jump into an individual block really easily because each block has the same size. Yeah, so two-step was telling me about this like segmented list iter in the standard library that we could have used. It's a little bit different, but very similar, but we're using this. So we need to implement swap remove. So I think that if we remove elements, say we have like allocated all of the blocks, right? And we start removing stuff. It means that like each of the inner blocks will have stuff allocated and we can't free them. If the whole point of this thing is to work with a bump allocator, we can't remove them. So like the maximum size of this thing will be like its size forever, right? Which kind of means that I think that our block here needs to say if he's allocated or not. Right? Because what we're doing here is we kind of like resize this slice as needed, assuming that we can. But yeah, I think we just need to say here items is the thing that we had before, and allocated is a bool. Which kind of blows. Maybe it means like, maybe we should separate this. It's actually better to separate it. So block allocated is something like this. And here we probably allocate block allocated is going to be a bunch of bools, and it's going to start at false. And then all we have to do is when we append a block here, we just have to check if the block exists. So if block allocated at old len, if this thing is not allocated, then we assign this thing. Otherwise, we just increase the blocks pointer. Yeah. Okay, that seems pretty reasonable. Then we have to set like self block allocated equals true. Dynamic bit set of managed would use less memory. Oh, that's a good point. I'm just gonna put a fix me on that because I don't want to think about it. But you're right. That there's no reason to do it this way. A waste of space, but we will live. We will live. Okay, so that should make it. I mean, we also should put a fix me on here that like test, right? But for now, we'll just kind of assume, and then let's do a swap remove. Okay. So index is a usize. I think there's no chance of failure here. And I think we just take like the last block, which right now assumes this thing. That's fine. That'll work. So we get the last block. And maybe we want this thing to be a pointer. We take the last element of this thing. So at this, like, you know, last element is this. We get the last element, and then we put this at index. Yeah. Okay. And then we just say that like last block dot len, last block is equal to last block dot pointer from 0 to last block dot len minus 1. And then I get a little bit worried about like reassignment in Zig. I've seen some bugs here. I'm probably just being a little bit superstitious, but I am gonna write old len here. Okay. Oopsies, last block dot len minus 1. We need to keep like a scoreboard of the longest name from the standard library that Two-Step has suggested as a proxy of specialness and therefore knowledge. Yeah, that's not a bad idea. It's pretty funny. Okay. So then all we have to do here is if the last block is now empty, if last block len is equal to 0, then we have to say self blocks is reduced by 1. Yeah. All right. Sure. Expected type bool found bool. Yeah, because I'm a dumbass. And at linked arrays list 79, this guy's mad because it's like this. All right. Index out of bounds. So here we have at 117, we are trying to... Oh yeah, we have to increase the size of the blocks first before we start inserting into them. That makes sense. Okay, so it looks like this is not working. So first of all, let's just do this for a second. Okay, that's not it. Not it. What are we doing wrong here? What are we doing wrong? We should probably GDB here, but okay, index 0, length 0. So that's a pretty clear indicator that we've done something fucking stupid. Can we GDB this thing? Usually it's like framing like 9, I guess here. So we're literally 0, 0. Self blocks length is 0. Okay. So why? Is this a result of our merge adjacent free segments? If we comment this out, is everyone else still happy? It does seem like everybody else is still happy there. So it's got to be a result of this, and it's likely that like we need to make sure to dodge ourselves. We're probably merging with ourselves and kicking ourselves out. So if I is equal to index, or if I is equal to IT, continue. We don't want to look at our own block. Okay, he's still unhappy, but now it's 1 instead of 0. So I guess now we have to bisect. So we're looking at block 0, item 1, and he's like, self blocks 0. Yeah, I mean, this is invalid. So I guess the question is why? So I guess it is time to try to write a test for removal. So let's do something where we, shove some shit in here. Let's just say that we have, block size of 5, and we will have 5 block, or a max size of 10. So then we only have to go over 10 things here. Then can we go like al swap remove 5. And then we should assume that we should get a sequence. Maybe we start with, yeah, we'll start here. We swap remove 5. So we should get a sequence of it should be 0, 1, 2, 3, 4, 9, 6, 7, 8. That's our new sequence that we should get. So let's see if this guy falls the fuck over. Expect equal that we get sequence at I is equal to al get I. Okay. Really? And if I do this, is that gonna fix it? Expected type usize got expected type. Oh, I need to write const here. True. Okay, so that's fine. So let's just start like removing a few more things. So if we remove like let's remove down to the block boundary, I guess. So like remove 2. After removing 2, it should be 8 and swap. Then we remove 1, and then it should be 7 and swap. So this is 0, 1, 2, 3, 4. So we need to remove 2 more. I don't know, we'll remove like 0. So this is a 6 swap. Can we do it like maybe like this so that sequence can be redefined? And then I don't know, remove 0 again. So now we should be seeing 9 like this, and this is now should be moved down to 1 block long. And let's do al.size in both of these to really just check how much we're fucking up. Okay. Okay. Okay, so that's good. That might want to use expect equal slices. The problem is that this isn't a slice. That's kind of the problem. So we can't do it that way, right? Because this is like a list of blocks. But I guess we could do it by like by block, I guess. But I'm okay doing it this way. Okay, so let's just like get all the way out. And I guess we probably want to also assert the size. So here we want to make sure that 9 is al size. Here we want to make sure it's 5. I guess we should test after 1 more swap because there's a chance of like block boundary issues. So let's put the 4 here, delete to here, put the 4 here. Okay. And then we remove the rest of them and we should be getting al size of 0. Okay. Is this gone GitHub? No, I'm not this part, not yet. But maybe one day. Okay, so it looks like at the very least removal is working fine. Now, can we just go, what if we just do 0 to 2 here? Run it twice, right? The idea here being that on the second iteration, this guy will, you know, he'll have some blocks that have already been allocated. So my guess here, based off the fact that this test is working, you know, we're not being too precise here, right? But at the very least, well, also let's just make sure here if we were to insert a bug in our test that it does get triggered. Yeah, okay, so it does. So at the very it seems like the swap remove part of this is working, right? So it's more my gut says at this point that it's more this like merge adjacent free segments that's being a problem. Right? And I'd be curious to see why. So let's run this again and try to look at where this is failing. This is failing on get IT, right? So is it possible that IT is ending up out of bounds? Yes, because if I is greater than IT here, it's moved back by 1. Right? Because if we removed something before I, now all of a sudden, no, his index should be the same. Am I stupid? I think it should be. Right? We have like, yeah, the only thing that can that can disappear is the back one, right? Because we have like 1, 2, 3, 4. I is here. IT is here. 4 goes into this slot. I is the same. I hasn't moved. So it seems fine. Maybe we start logging stuff. And then here we say removing this. I guess we kind of know implicitly it's IT that we're moving, so we don't have to write that down. So we start at 34, we start bouncing back between 0 and 1. And then eventually we removed so much that we're like donezo. It's because we need... Let's maybe write what we're merging. Or maybe we could even like print the free list at this point. That might be kind of interesting. Okay. This is kind of hard to process. Let's write down what we're merging, I guess. Oh, wait. I guess if we didn't merge, we should only swap remove if we merged. Yeah, this is stupid. We're going over every single element, and we're swap removing everything. So it should be like... Yeah, it should kind of be like this. I think. Okay, we're still crashing, but now this feels a little bit less stupid. So now if we make it through every single element, we should break. But that's not happening. So here we go, like we're 34, 35, 33. We're doing a lot. We're doing a lot. Can we... Size will be changing in the loop, right? Did I miss that? Only if we do this though, which means that we should break out of the loop after. Right? We should immediately go back up here and recheck the size. So I think it's okay. I think. What happens if we just don't do this? We only allow one iteration of merging. Okay, so that works okay. And so it looks like the problem, at the very least, it's to some point, to some extent, is coming from the merging of blocks. Or the recursive nature of this thing. So if other start equals our end, we increase. We remove ourselves, which is fair because we just merged in here. And then we go again, looking at the guy that we just merged into. That seems fine. If other's end is equal to our start, other end equals our end, okay, then we do the same shit. And then if we make it out, we break. Oh, okay, wait, hold on. So it is only like a couple iterations for most of these. Then on this, some version of this guy, we're freaking the fuck out. Oh, it's we need to do if I is equal to self free list size -1. We only update this thing if it's different, because otherwise we'll have swapped it into the place that we were previously looking. He didn't like that. If I is not equal, I thought that would be it. I thought that would be it, right? Because here we're seeing, we go 36, 33, 35. But we've just removed the thing at 35. So, like, why is this a problem? -2? No. Oh. It's after removal. It's after removal. Okay, there we go. So now we got something. How's our... Oh, that's so much fucking better. Look at that. Look at that. That's so much better. I should have fucking backed up the old version. But look at that. That's... Before we had, like, so much shit down here. It was like a page of shit. And now, I mean, there's still clearly wasted space. But it's not that bad. Not that bad at all. All right. Cool. So I guess we kind of spent a lot of time at some point working on defrag. Now I guess this means that we will spend tomorrow on buddy system because it's 350. But that means tomorrow we can kind of compare the performance of this like naive, stupid version of this thing to using the buddy system to try to like more intelligently track how things are connected. We also might have to be a little bit careful about I don't know how we're going to track allocations in a way that is like, we're gonna need like some sort of like sorted list of free segments. So maybe the next step here is actually to try to implement some sort of like B tree for these things, or sorry, B tree or red black tree, some sort of tree structure in order like to track the free segments and kind of compare performance of that. But pretty good success for today. Pretty good success. What did we do? We built out a little bit of tests. Is free potentially something like O(n) squared now? Where n is not, n is something. But yeah, it does seem like pretty n squared right now, right? Because the merge blocks are going to, it's probably more likely. Every time you remove one, every time you merge a block, it goes down a little bit. So definitely not all the way up to n squared, probably n squared like. In like, it's probably, I think O(n) squared is correct. But n is like the number of segments in the free list, which is probably different than something. But yeah, I agree. Yeah, so what do? We built out this like test system that lets us like allocate a bunch of shit of different sizes. We added this like, we looked at the like efficiency of this thing, which I guess actually we can probably compare pretty easily by just commenting out this merge adjacent free segments, right? That's essentially what we were doing before. Yeah, so before we were looking at like, we had like around 700k free, but we only had 100k, like 170k allocated. Now it's literally like 26k, like just sitting around with 170k. It's way better, way better. Yeah, so we built this inspection. We had the visualizer, which is looking pretty good. Then we did some defragging. And that took us a little stream. So pretty good, pretty happy with that. Thanks for watching, guys. If you like what you saw, we stream most days at around 12:30 Pacific time to 4 o'clock Pacific time. It is 4 o'clock Pacific time now. So if you're watching live, 3.5 hours ago to now. If you're watching live and you're like, I would like to keep up on this, there's a YouTube link in the Twitch description. Videos are organized in the playlists. This is kind of sitting under the Mizik playlist right now. It's likely that this will move into some sort of like allocation playlist soon. I will not be streaming tomorrow. I will be back the next day to do implementation of, trying to improve the efficiency of this thing. Yeah, I think that's it. YouTube, peace out. Twitch, let's find someone to raid.